The Pentagon is preparing for a computing revolution unlike anything before, and this revolution could reshape America's entire defense infrastructure. Quantum computing is moving from theory toward strategic importance. Military planners are increasingly studying its potential consequences, but quantum technology creates opportunities and dangerous new vulnerabilities. That combination makes quantum computing unusually important for defense. Imagine computers solving problems conventional machines struggle to handle. Some calculations could eventually become dramatically faster using quantum systems. That possibility has enormous implications for military planning. It could influence logistics, optimization, sensing, and scientific research. But there's another side of this technological transformation. Powerful quantum machines could threaten today's encryption methods. Military communications depend heavily upon secure digital infrastructure. Intelligence systems also rely upon protected information exchanges. A future quantum computer could challenge some existing cryptography. That possibility has forced defense agencies to prepare early. The Pentagon therefore faces two quantum problems simultaneously. First, it must explore useful quantum capabilities. Second, it must protect systems against quantum-enabled attacks. Those goals require different technologies, strategies, and timelines. This is where post-quantum cryptography becomes extremely important. Post-quantum cryptography aims to resist future quantum attacks. It protects information without requiring everyone to own quantum computers. The defense establishment is already planning migration toward these protections. Recent official strategy documents emphasize deliberate preparation. That means quantum security is becoming an infrastructure issue. It isn't simply a laboratory experiment anymore. Nearly every modern military system depends upon digital technology. Aircraft, satellites, networks, databases, and communications rely heavily. Protecting those systems requires understanding future technological threats. Quantum computing could eventually change the cybersecurity equation, but experts emphasize that major quantum capabilities remain developing. Today's quantum computers still face substantial technical challenges. Building reliable systems requires solving difficult engineering problems. Quantum states can be extremely sensitive to environmental interference. Errors therefore remain a major obstacle for researchers. Scaling quantum systems presents another enormous challenge. Yet defense planners cannot simply wait for perfection. Cryptographic migration can take years across massive organizations. Military networks contain countless systems and connected technologies. Replacing cryptography across those systems requires careful coordination. Some information also needs protection for decades. That creates urgency even before powerful quantum computers arrive. Adversaries could potentially collect encrypted information today. They might attempt decrypting that information much later. This concept makes quantum preparation especially strategically important. Defense leaders therefore need technology and security simultaneously. Quantum research could eventually improve difficult computational tasks. Logistics represents one potential area of interest. Military logistics involves enormous numbers of possible decisions. Optimizing routes, resources, and schedules can become extremely complex. Quantum algorithms may eventually offer advantages for selected problems, but those advantages aren't guaranteed for every military calculation. Quantum computers won't simply replace conventional computers everywhere. Instead, they may become specialized tools for certain problems. That distinction is crucial when discussing military quantum strategy. The Pentagon also studies quantum sensing and related technologies. Quantum sensors could potentially improve extremely precise measurements. Such capabilities could matter for navigation and detection. They could also influence future battlefield awareness systems, yet these possibilities remain areas of active research. Defense agencies must separate realistic capabilities from speculation. That's why current strategies emphasize research and preparation. Another major challenge involves developing specialized quantum talent. Advanced quantum systems require highly trained technical teams. Defense laboratories are therefore building specialized research capabilities. Universities and industry also play important supporting roles. Government research programs increasingly commit. The biggest quantum concern may not involve faster calculations. It could involve something much more fundamental: encryption. Modern defense systems depend upon cryptography almost everywhere. Encryption protects messages, databases, credentials, and sensitive information. It helps keep military communications away from unauthorized observers, but quantum computing could eventually change those security assumptions. Certain quantum algorithms could challenge widely used cryptographic systems. The threat isn't necessarily immediate, however. Building a sufficiently powerful quantum computer remains extremely difficult. Researchers still face major problems involving errors and scalability. Quantum systems require extraordinary control over fragile quantum states. Even small disturbances can interfere with computational results. That's why useful large-scale quantum machines remain challenging. Yet defense planners cannot simply wait for certainty. Cryptographic systems take enormous effort to replace across networks. Military organizations operate thousands of interconnected digital systems. Many systems also contain equipment designed decades earlier. Updating every security mechanism can therefore become extremely complicated. Some sensitive information requires protection for many years. That creates an unusual cybersecurity problem today. Information captured now could potentially become readable later. Security researchers sometimes describe this as harvest now, decrypt later. The idea sounds futuristic, but preparation happens today. Defense organizations therefore need quantum-resistant security before quantum machines mature. This is where post-quantum cryptography enters the strategy. Post-quantum algorithms are designed to resist quantum attacks. They can operate using conventional computing infrastructure today. That makes migration possible before large quantum machines arrive. But migration itself isn't a simple software update. Organizations must identify vulnerable systems across complex environments. They must understand which algorithms those systems currently use. They also need replacement technologies that remain secure. Testing becomes essential before changing mission-critical communications. A failed migration could create unexpected security weaknesses. That's why planning becomes almost as important as technology. The Pentagon's challenge extends beyond computers inside buildings. Military networks connect aircraft, ships, satellites, and ground systems. They also interact with contractors and external infrastructure. Every connection can introduce additional cryptographic dependencies. Finding those dependencies can become a massive organizational task. The longer migration takes, the greater uncertainty becomes. Meanwhile, quantum research continues advancing around the world. Governments increasingly view quantum technology as strategically significant. China, Europe, and other nations invest heavily too. That creates another layer within America's quantum planning. The issue isn't simply who builds the fastest machine, it also involves who develops useful applications first. Whoever integrates quantum capabilities effectively could gain advantages. Those advantages might emerge across science and defense, but technological leadership doesn't guarantee immediate battlefield superiority. Quantum computers still need practical applications and reliable hardware. That distinction often disappears in sensational headlines. The real story is more complicated and fascinating. Defense planners are preparing for multiple possible futures. One future involves quantum computers becoming broadly useful. Another involves specialized quantum systems solving narrow problems. A third involves quantum sensing becoming more practical. And every scenario includes cybersecurity consequences. This uncertainty explains why research remains strategically valuable. You don't need perfect predictions to prepare responsibly. You need flexible systems capable of adapting quickly. That principle also applies to military procurement decisions. Hardware purchased today may remain operational for decades. Designers, therefore, need to consider future security requirements. Otherwise, today's systems could become tomorrow's vulnerabilities. This becomes especially important for classified information. Sensitive data can remain valuable long after creation. Military intelligence may retain strategic importance for decades. Protecting that information requires long-term cryptographic thinking. Quantum computing therefore changes cybersecurity planning horizons. Security teams must think beyond. Quantum computing gets attention, but sensing could matter sooner. Quantum sensors could measure extremely small physical changes. That capability could eventually influence several military applications. Navigation is one especially interesting area for researchers. Modern forces rely heavily on positioning and timing systems. Satellite navigation provides critical information across many operations, but satellite signals can become unavailable or disrupted. That creates demand for alternative navigation technologies. Quantum sensing could potentially contribute to that solution. Some quantum sensors detect changes in acceleration extremely precisely. Others can measure magnetic fields with exceptional sensitivity. These measurements could support advanced navigation techniques. They might also improve certain detection capabilities, but laboratory performance doesn't automatically translate into battlefield readiness. Military hardware must survive vibration, temperature, and harsh environments. It must also operate reliably outside controlled laboratories. Engineers therefore face difficult practical challenges ahead. Size and power requirements can become important constraints. Cost matters too when technologies must scale across forces. Reliability becomes especially important for mission-critical equipment. A sensor providing incredible precision means little when unreliable. That's why quantum development involves more than scientific breakthroughs. Researchers must transform fragile experiments into dependable instruments. This transition can take years of engineering development. Yet potential benefits keep defense organizations interested. Consider navigation when satellite signals become unavailable. Conventional backup systems can accumulate errors over time. Highly sensitive sensors could potentially reduce those uncertainties. That could matter for aircraft, ships, and other platforms. Underwater navigation presents another particularly difficult challenge. Submarines cannot continuously depend upon conventional satellite signals. Precise onboard measurements therefore become extremely valuable. Quantum sensing could potentially support future navigation research. Another possibility involves detecting subtle environmental changes. Extremely sensitive measurements could reveal otherwise difficult signals. Researchers are investigating applications involving magnetic and gravitational fields. These capabilities remain subjects of ongoing scientific development. Their eventual military value depends upon practical implementation. That distinction separates serious analysis from exaggerated predictions. The Pentagon isn't simply buying magical quantum machines. It is investing across research areas with uncertain outcomes. Some projects may eventually become highly valuable technologies. Others may remain useful primarily within scientific research. Strategic planning must therefore manage uncertainty carefully. This is particularly important when technologies evolve rapidly. Quantum research involves several competing hardware approaches. Different approaches offer different advantages and challenges. Superconducting systems represent one major research direction. Trapped ions represent another important approach. Neutral atoms have also attracted significant scientific attention. Photonic approaches provide another possible pathway. No single architecture has guaranteed future dominance today. That uncertainty complicates long-term defense investment decisions. Officials need flexibility, while the technology continues evolving. They also need access to emerging scientific expertise. This makes partnerships with universities particularly valuable. Private technology companies also play a major role. Commercial quantum research can accelerate hardware development. Government programs can then explore specialized defense applications. Together, these efforts create a broader innovation ecosystem. But quantum sensing isn't happening in isolation. It connects directly with broader defense modernization efforts. Modern military operations increasingly depend upon precise information. Better sensing can improve decisions before actions begin. Faster information can influence planning and operational awareness. Quantum technologies could eventually contribute to that information advantage. Yet information alone doesn't guarantee strategic superiority. Military systems must interpret and act upon measurements. That requires software, communications, and trained personnel. Quantum sensors therefore need integration with existing platforms.